Thank you for that kind introduction, and I'm very pleased to be here today to give this second keynote. And I'll be talking about the statistical advantages of MAIHDA for estimating intersectional inequalities. So in the first keynote, we've already had an introduction to MAIHDA, and indeed an argument as to a future direction in which we can take it. That we've also had one of the two parallel sessions had a couple of talks on MAIHDA as well. So if you were in that one, you've had quite an exposure already. And here is another talk again. But each of these talks is, of course, slightly different. Now, the difference in my talk is that I'm really going to look at the purported statistical advantages of MAIHDA over traditional descriptive statistic approaches to estimating intersectional inequalities. And there was one talk in that parallel session, the very last one, which was taking a simulation study based approach. I'm going to do something different in this one. I'm going to actually look at analytic expressions for the different statistical properties of these inequalities that we're going to look at. And I hope that will kind of explain what's really going on here, because ultimately these MAIHDA analyses, the underlying statistical models are actually quite straightforward, multi-level models, and we can look at all of that literature and work with those models to really see what's going on with MAIHDA. So I'm trying to kind of bring some clarity to this analysis, and we really need that kind of strong base if we are, as Anne suggests, to take MAIHDA further with cross-classified analyses and so on. We've really got to understand the basics fully. So that's what I'm speaking to. Okay. And so I should say that my own background is that I do a lot of multi-level modeling development and applications and training and so on. I don't have a background in intersectionality at all, except that maybe for the last 5, 6, 7 years or so, I've been working with others who are really interested in intersectionality, supporting them in the development and the use of MAIHDA. So that's my background, where I'm coming from here. And I'm really looking forward to hearing your response to what I'll show you, and hopefully find ways to improve MAIHDA further. So let's look at the outline of the talk. So as with some of the other talks, I will kind of gently lead into MAIHDA from regression to MAIHDA, and each of us kind of motivates it slightly differently. But I'll quite quickly get into an illustration of MAIHDA, and that's going to be taken from the academic literature, a published paper in education, and I'll use that to motivate the real content of this talk, which is about the statistical properties of different ways of mapping and reporting intersectional inequalities, and trying to get to the bottom of some of the statements that people have made in favour of MAIHDA. And we've got several sections on that, and then I'll conclude. So first of all, from regression to MAIHDA. So let's start really simple. So a very traditional approach, not the only one, but a very standard approach to studying intersectionality with individual outcomes would be to run a regression of the outcome of interest on various socio-demographic characteristics. So these might be gender, socioeconomic status, ethnicity, and so on. Often people are very interested in combinations of those characteristics, hence the name intersectionality, the intersections of those characteristics, and they try and capture that in the regression framework by introducing interactions. Typically, they'll introduce a particular two-way interaction of interest, given their substantive focus or theory or the literature that they're drawing upon. Maybe they even consider a couple of these. They're very interested in talking about departures from additivity, that something unique or different is happening for particular combinations or intersections of characteristics. So I've written out a regression equation there with 3 characteristics, x1, x2, x3, which might be gender, socioeconomic status, and ethnicity, very crudely in terms of 3 binary variables there. And you can see even with 3 characteristics, you're going to get 3 two-way interactions and 1 three-way interaction. And any permutation of those could be explored, but typically it'll be 1 or 2 selected two-way interactions. Now, a critique of that is that we may miss the very complexity that we're interested in intersectionality, because it's only very partially exploring all the possible intersections going on. we're knocking out those terms I've done a red line through by not fitting all possible interactions. Again, then you run the risk of failing to make visible what's really happening at different combinations of characteristics. And ultimately, we could be mischaracterizing inequalities. And this might mean from a policy perspective that we go on to suboptimally targeting particular intersections. And the real worry is that it's multiply marginalized groups where we might not really see what's going on, and we might not be giving the right targeting of whatever we're doing to them. And this can ultimately harm individuals and society. Okay, so given that argument, then one response would be, well, let's just estimate all possible interactions and do what's called a saturated model. And here you can see I've now kind of switched on the extra two-way interactions, the three-way interaction. The problem is that already with three characteristics, gender, socioeconomic status, ethnicity, we're arriving at a model which is substantively very hard to interpret. It's very hard to interpret what beta 5 is, what beta 4, this should say beta 7 over here, what beta 7 is, and so on. Also, some of these multiply marginalized groups can be pretty small. And so what this means is that some of those interaction terms can end up being rather erratically estimated, a bit all over the place. And also with many, many parameters, particularly when you expand from 3 to 4 to 5 sociodemographic characteristics and the corresponding increase in the number of interaction terms, you run the risk of hitting false positives as well there. So there are some drawbacks to that saturated approach, which would be natural to turn to. And indeed, I've said with 5 binary social identities, we'd have 10 of these two-way interactions, 10 of these three-way interactions, 5 four-way interactions, and 1 5-way interaction. Okay, so a response to that is, well, let's not try and interpret the individual betas here. Let's just use this saturated model to estimate the mean outcome at each intersection, okay? And so because it's saturated, you'll estimate a unique mean for each and every intersection, and then you could just map those in a kind of a league table. Now, sometimes that's done more simply just by putting in a dummy variable for each possible intersection. Now, with 3 binary variables, you'll get 8 intersections, and so you put in 8 dummy variables, and you just estimate their coefficients with no intercept, and you get their means directly. Even more simply, if that's all you're going to do, you might just calculate with descriptive statistics the mean at each intersection. So what I'm trying to show you is kind of some of the standard things that people might consider when trying to kind of map out what's going on at different intersections, and some of the issues in doing things. So there's kind of classifying approaches that we've talked about so far. MAIHDA is a fancy name, stands for multi-level analysis of individual heterogeneity and discriminatory accuracy, the world's longest acronym. But it's really just an application of two-level multi-level modeling, a two-level linear regression. And the levels in this linear regression are individuals at level 1 nested, not within schools or neighborhoods or other organizations at level 2, but nested within their intersections, where those intersections are defined by the unique combinations of the sociodemographic characteristics of interest, let's say gender, ethnicity, and social class. And interest lies in terms of how the mean outcome varies across those intersections. And we'll talk a lot about how this is different from what we've shown so far. Now, what people are trying to get out of this MAIHDA analysis are 4 things. They're trying to, first of all, quantify what is the overall importance of intersectional inequalities. You know, to what extent are individual outcomes patterned by these inequalities across whatever the 8 intersections? Secondly, can we predict what the mean outcome is in each and every intersection? Okay, use the sample data to predict optimally what's going on in the population. Can we rank those intersections? And then once we've done that exercise, to what extent are those intersectional inequalities, do they have a kind of an additive pattern or structure to them versus departures from additivity? And that's speaking to this idea that there could be unique things happening at particular combinations of characteristics. Now, if in general we are finding some non-additivity, then of course you want to know, well, where is that non-additivity? And that is the fourth goal of MAIHDA, if you like, which is to decompose each and every intersectional mean into that part which we kind of expect based on a hypothetical additive world, where we've got the additive risk factors, if you like, for the outcome in terms of gender, socioeconomic status, ethnicity, and departures from additivity, the unexpected part, which is substantively often very limiting to people. So that's what MAIHDA is going to do. So I should say at this point that MAIHDA was proposed in a paper by Claire Evans, a co-author of mine in 2018, coming out of her PhD, supervised by Subramanian, another colleague of mine. That was a 2018 paper, that's the original reference, if you like. But if you want to learn more about MAIHDA, then this tutorial article, which Claire, myself, Subramanian, and Andy Bell and Juan Merlo were all co-authors on, provides a very nice tutorial paper with R scripts and status scripts and data sets and so on. But what I'll be largely talking about today is going to be taken from a recent working paper of mine with the same kind of co-author team. And this is the statistical advantage of MAIHDA for estimating intersectional inequalities, which is the same name as this talk. And that's up on SOC archive if you want to look at it. Okay. So let's kind of illustrate MAIHDA, and we'll use this to motivate the analytic expressions that I'm going to plot later on to try and get to the bottom of why people think MAIHDA is better. Okay. So the illustrative application I'm going to show you is taken from a nice paper by Lena Keller, who was, I believe, also a PhD student working in Germany under Oliver Lutt, who's a well-known quant methodologist. And she was the first application of MAIHDA in educational research, which is actually my applied research area. So in her analysis, she reanalyzed PISA data on German 15-year-olds and their reading scores. So essentially, the PISA data, children in all different countries around the world take tests at age 15, and you get these international league tables of how countries are doing. But she focused just on Germany. And the socio-demographic characteristics she was interested in were gender, 2 categories, immigrant status, native immigrant, education, whether your parents are high school educated or further, they have university education, and the occupation of the parents in 5 categories, low through high, and either just 5 quintiles of the population. There's some 5,400 students, and because we have 2 by 2 by 2 by 5, that's 40 intersections, and those are our level 2 units in the multi-level analysis. So those are just some descriptive statistics, not really saying anything surprising. We see for reading at age 15, girls do better than boys, native students do better than immigrant, university-educated parents, their children do better than those who left education earlier, and there's an occupational gradient, whereby higher occupations have higher reading scores. Okay, this is a nice graphic from that Lena paper, and you can see she calls them strata or stratum. We've done so in previous papers. I mainly call them intersections. But the very first one in the data is gender is female, immigrant status no, parental education high school, parental occupation low. And there's 123 of those students, and they're in that first cluster of intersection. And we're interested in their mean outcome. And then you can cycle through all 40 of these intersections. You will end up at intersection 40, which are now males. Yes, they're immigrants. They've got university-educated parents and who are in high occupation jobs. And that's the last intersection. And we're interested in mapping out the inequalities and mean outcomes across those intersections. Okay, so this brings us now to the first MAIHDA model. Now, this is just what in multi-level modeling we'd call a 2-level empty model with a continuous outcome. You might call it a 2-level variance components model, 2-level random intercept model, all of that kind of jargon. That's what we're talking about. So in terms of the algebra on the model equation, we have y sub ij, which is the reading score for child I in intersection j. And that's modeled in terms of a mean outcome, mu j, which is an unknown latent variable. This is the quantity of interest. What is the population mean outcome amongst those kids in the population at large in that intersection? We only have sample data, and so we're going to try and estimate or predict it. And then obviously the observed score for any child deviates from that, and that's your conventional residual. Now, what's important is how we specify a submodel for these population means, because we're going to have two MAIHDA models. Now, this first one is very simple. We just say the mean outcome at intersection J is simply equal to the overall mean, which you can think of as the German national average, plus a deviation of that intersection mean, that mu J, from the German average. Okay, so yeah, that's just how it goes. But later on, we're going to build a more complex regression model in there. But this first model is going to give you the first two aims of MAIHDA. We're going to get something called the variance partition coefficient, which quantifies how much variance is at level 2 between the intersection means. And that's going to be an effect size metric for how important are intersectional inequalities. And that's just going to be the variance of these intersection mean deviations divided by the total outcome variance. So it's basically the variance of the intersection means as a proportion of the total. That's going to give me the first thing of interest. Now, the second thing of interest, which is what is the intersection mean at each and every intersection? Now, this is really crucial for this talk, because what we see from this equation here is that it's more complex than the simple descriptive statistic mean, y bar j. Okay? And so people often argue that MAIHDA gives you better predictions of the intersectional inequalities due to something called shrinkage. Well, this is what they mean by that. Okay? Because the predicted mean for a given intersection is actually a weighted average of the observed mean in the sample and the estimated overall mean, beta 0. And because it's a weighted mean, that mu j prediction will lie between the observed mean and the overall mean. And that means it gets shrunk towards the overall mean. And that shrinkage is considered desirable because we're going to get more shrinkage when we have intersections with very little data. Why did we get that? Because the weights in this weighted average, the R sub j's, are a function of sample size. And those RJs are often referred to as the reliability. What reliability? Well, it's the reliability of using the observed mean as a predictor of the true mean. And that reliability can range from 0 to 1. The higher the reliability, the closer it is to 1, the more we'll use that very reliable observed mean as the basis for our prediction. But the less reliable it is, the more we'll actually emphasize the overall mean as adding information to what's really going on in the population. And so you can see the sample size is sitting down there, that NJ. So if you only have a handful of individuals at a particular multiply marginalized group, then actually the best prediction that we can make for their mean outcome in the population at large is not going to be the sample mean off the back of a few randomly selected individuals. It's going to be some optimal reliability weighted average of that in the overall mean. Okay. So I'm going to show you some of the statistical properties of calculating the predictions this way versus just reporting the y bar j's. But returning for a breather to the results from Keller's initial analysis, she found in that empty model that the overall mean in Germany is 478, and she found what is the importance of the intersectional inequalities. Well, they're accounting for 16% of the variance in student scores around that overall average. Therefore, 84% is happening within the intersection. So within any given intersection, each kids are very diverse. Okay, nevertheless, the intersections matter, and the top ones are doing noticeably better than the lower ones. So that brings us into the second thing you get off the back of that first model, which Keller presents, which is the predicted mean. And these are those reliability weighted averages. So these are argued to be better than the observed means, but no one has actually really shown how much better they are and in what circumstances. And that's still to come in this talk. But what we can see here are the 40 means being plotted, red for girls, blue for boys. The range goes from about 420 to around 570. That's a 150-point range. Now, the weird and wacky scale for reading scores here, 100 points is basically a standard deviation. So even though these intersectional inequalities only account for 16% of the variation in individual outcomes, we do have a 1.5 standard deviation range from the bottom to the top of that, a distribution of 40 intersectional means. So there is meaningful action going on. You can see the labels across the top, which is describing those 40 means and how they differ from one another in terms of education and occupation and immigrant status. But something else you can see here is that there is some hinting that there could be some non-additivity, some what you would call traditionally interactions going on. We see in general, girls do better than otherwise equal boys. The red dot is higher than the blue dot for each combination of ethnicity, occupation, and immigration that we are showing. But you know, sometimes the red is noticeably higher than the blue, and occasionally somewhere it flips around. Here it's flipped around. Also, we see kind of so it looks like there could be some non-additivity. The gender effect depends on the other characteristics. Also, the occupation effect, which is the kind of the slope that we see across 5 occupation bands holding, let's say, education and immigrant status constant, is rather shallow here, and it's steeper here. So model 1 is hinting at some non-additivity. So this is what model 2 is going to go on to explore. We've got much wider confidence intervals, I should say, for some intersections than others, and that's where we have far less data as well. So we'll see more. This shrinkage would have hit these guys more than those ones, I should say, as well. Now, model 2 extends model 1 by effectively putting into the model the main effects of the sociodemographic characteristics which we use to define the intersections. So those were gender, immigrant status, education, and occupation, and dummies have gone in for the categories of each of those variables. And so what that means in this model here is the right-hand side's changed. The left-hand side is still the true intersection mean of interest, but now, rather than being modeled in terms of a single overall mean for Germany, we've now got this additive structure here. And so this is going to give you the predicted mean outcome based on the additive effects of gender, ethnicity, occupation, and education. Now, that's not going to perfectly get us to the means, because we know there's some non-additivity going on, and that's captured by this random effect over here, whose interpretation is now how the true intersection mean deviates from additivity rather than the German-wide average. And then we want to kind of answer the third question, which MAIHDA gives us, which is, well, just how additive are this league table of intersection means? And that's saying, to what extent are these intersection means explained by this part versus that part? So if you do the variance of this divided by the total variance, the variance of this plus the variance of that, that gives us a measure. And that's often called the proportion change in variance, because you can also estimate it as the reduction in the random effect variance, the shift from the previous model to this model. So there's different ways to arrive at the same thing. But that's a second kind of effect size metric, which all MAIHDA studies report. And whereas the VPC is often 10, 20%, this is often more like 80, 90%, 95% in most applications. So most intersectional inequalities are largely additively patterned, but not completely. Now, this brings us on to an interesting thing, because just like in the last model where post-estimation you could predict the mean outcome at each and every intersection, you can do that after MAIHDA model 2 as well. But the formula is different. Okay, we've still got a weighted average, a reliability weighted average of the observed mean. But now we're not weighting that as an average with the single value for the overall German average. Rather, we have the predicted mean for the intersection in question based on this hypothetical world of additivity. So the observed means get shrunk towards our expected mean based on additivity. That's a nice thing to do, because the expected mean is based on all the data, whereas the observed mean is just based on a handful of students we might view at a particular intersection. It's still a reliability weighted average, but note, whilst the reliability formula is the same, the value of sigma u squared has plummeted from model 1. So actually, these are conditional reliabilities, and R is much smaller than before. So now we're giving less weight to the observed mean than in model 1 and more weight to the model, because the model is better informed than in model 1. So this is going to give us our third method for constructing a league table of intersection means. We've got the wide bars, we've got the predicted means from model 1, and now we've got the predicted means from model 2. So there are going to be 3 different methods. This is going to be the one which would seem to be the best, but we need to kind of explore why that might be and just how much better it really is. But before we do so, here are just the results from Keller. So she found that, hey, those additive main effects accounted for 91% of what's going on. Okay, just 9% are deviations from additivity. So from a conventional linear regression perspective, we're kind of saying that 9% of the variability is due to two-way and higher way, two-way, three-way, four-way interactions, if you like. So statistically, model 2 is definitely preferred. Okay, we've got a meaningful amount of departures from non-additivity. But if we plot those departures from non-additivity, as Keller does, what you'll then see is actually only 1 in 40 of those comes out as statistically significant. And that feels a bit of a contradiction, because we said the model as a whole is much better than model 1, but actually in terms of these deviations from additivity, it looks like we can't get much out. And that's because this is a much harder thing to do from a power perspective, because there isn't much data on any given intersection. And so it is perfectly possible to say that, hey, intersections in general deviate from additivity, but we can't really isolate which particular intersections are doing it. And that's the kind of scenario that we're in with this particular data set. Oh, sorry. Having said that, we're seeing that 6 of these 40 intersections deviate by 10 points or more, which is a 0.1 of a standard deviation or more. And indeed, the one significant one, that's about, I'd say it's about 20 points. So that's 0.2 of a standard deviation. So it's effectively girls, it was native German girls who have highly educated parents in high occupational status score even higher on reading than what we might expect, given the beneficial additive main effects associated with those characteristics. So that there's for whatever reason, there's something extra going on there than what we've expected, given the data at large. Okay, so let's kind of finally, after a rather lengthy 28-minute warm-up, get into which intersection means are the best to report. So first of all, here is me plotting the Keller results, and we can see that the simple means, so what we've got here are the predicted means on the y-axis. The 3 methods I've mentioned are below: the simple means for the 40 intersections, the MAIHDA model 1 means, and the MAIHDA model 2 means. And I've highlighted the 6 intersections which have 20 or fewer individuals in these data. And they are the ones whose values for the predicted mean move around the most as we shift across methods, because that's where there's the least data and they're most sensitive to method. The vast majority of intersection means aren't moving around much at all, because they have healthy number of students. And so whatever method you use, you get very similar answers. And that's a really important take-home message. Okay, so some of the purported advantages of MAIHDA really come into their own when you have small intersections. But if you have a data set where even the smallest intersection's got 50 or 100 individuals, it's really not going to matter which of these methods you use to construct your league table. Having said that, often we are particularly interested in the multiply marginalized groups, which are those with the fewest individuals. So actually, in a lot of analyses, there aren't that many people in the intersections which are most important to us. And indeed, here we can see I've got 2 intersections with only 3 people, despite the overall sample size being 5,400. Okay, and there are those ones there. The other thing to notice here is that the variability in those predicted means is noticeably less in MAIHDA models 1 and 2 than the simple means, and that is that shrinkage idea controlling the statistical noise, sampling variability, which is very dominant in the simple means, problematically leading smaller intersections to disproportionately appear in the tails of the distribution, all else equal. Okay, so we zoom in now, let's say on that purple line in section 37. Okay, it's got 3 different scores. The scores are 463, 468, 497 for simple means MAIHDA model 1 and MAIHDA model 2. Now that range is some 34 points, which is 0.34 of a standard deviation. So it really does matter substantively which method you're picking. And the range of values for the purple is by no means the biggest range of values. Some of the other intersections see an even greater range. And this is the one that we're going to focus on. So mechanically, what's going on? Well, this is my attempt in the paper to kind of show you mechanically what's going on. In the simple approach, in blue, we just have the simple mean, Y bar. This is if you just take the 14 kids, I believe it was. Yeah, the 14, 15-year-olds at that intersection, you average their reading scores, you get 463, and you're done and dusted. Now, the MAIHDA model 1, what it gives you back is 468. Now, that's a weighted average of the observed mean of 463 and the German average of 478. And it's a reliability weighted average. The reliability of the observed mean is 0.73. Okay, it's not that high because you've only got 14 kids. If you had more kids, that reliability would go up and that green dot would approach the blue. And if you had fewer kids, 13, 12, 11, 10, all the way down to 1 to 0, you'd end up at 478. So that's how it kind of slides around the green dot, what's actually pumped out from MAIHDA. What then is MAIHDA model 2? Well, MAIHDA model 2 does that reliability weighted average of the observed mean, 463, but now it doesn't shrink it towards the overall average of 478. It shrinks it towards whatever the model implies for that intersection based on the included additive main effects. And for this particular intersection, 37, which was native males with low educated parents, yet they're in high occupations, a little bit unusual, hence a small number of individuals, we see that they've actually got a very high predicted mean based on the additive effects. And so even though we observe something lower, far lower than what we'd expect, we think that's pretty unreliable because we've only got 14 kids and get shrunk massively up to that. So mechanically, that's what's going on. But let's finally get into the analytic results, which kind of statistically will argue that model 2 is the best of these 3 approaches. So the first thing I do is go on doing analytic expressions rather than a simulation study. I still declare a model to be the true model, just like you do in a simulation study. And I say it's model 2, okay? And we consider 3 sets of means. And that's not a controversial thing to do, really, because model 1 is just a constrained version of model 2. And even in some senses, the simple means is a kind of constrained version of model 1. So they're kind of nested in a sense. So it's not, I don't consider that a particularly problematic setup for this. But what we do here is we, first of all, consider the entire distribution of intersection means and what is their variance, and how does that compare with the true variance. We know the truth because we are playing God by doing analytic expressions, just like you would in a simulation study, but also how correlated are the means from each of these methods with the true means, and obviously we want a correlation of 1. Now, to do this, we obviously have to kind of declare the characteristics of the true model. And by that, I mean, we have to declare how important are intersectional inequalities in the first place. And I say they account for 15% of what's going on, similar to the Keller study. And then we also have to say, to what extent are the intersectional inequalities additive? And we're going to say 90% additive, again, similar to the Keller study. And what we do is we derive what is the variance of the observed means or simple means, what is the variance of the model 1 predicted means, what is the variance of the model 2 predicted means, different algebraic expressions. But armed with that algebra, we can plot what's going on and see. So in this setup, the true variance between those intersection means is 0.15, the black horizontal line. And we're interested in how the blue, red, and green lines, how close they can get. The blue, the simple means, are always going to overstate how different intersections are from one another. They're going to overstate intersectional inequalities. And that's because you've got sampling variability in those means. And that's particularly problematic when intersection sizes are small, okay? And down here, I've got 25, 10, and that's when it's particularly problematic. Now, model 1, the red line, MAIHDA model 1 shrinks all of those observed means towards the German average. And so in doing so, actually, it's very conservative. And so we understate the extent of inequalities. But I should say, of course, we directly estimate it from the model parameters. So that in itself is not actually so problematic. But the green line gets those intersectional inequalities much closer. And that's because it's model 2 and it's shrinking towards the additive main effects. Now, crucially, the differences between all three methods basically disappear when you have a very large data set where even the smallest intersections are sizable. But as I said, often that's not the case, and particularly because the ones of most interest are pretty small, they're multiply marginalized. Now, in terms of correlations with the truth, again, we've got to derive some algebraic expressions. We plot them. Here, we want our blue, red, and green lines to be as close as possible to the correlation of 1, the black line. So the blue and the red lines are actually on top of each other in this setup because I've done this for the balanced data case. In the paper, we could also consider imbalance. But in the balance case, actually, the MAIHDA model 1 gets you no closer to the truth than the observed. And that's because when the data are balanced, all the intersectional means are shrunk by the same degree because the shrinkage factors are identical or the reliabilities are identical. But in a more realistic scenario where some intersections are larger than others, you'll get differential shrinkage. And actually, in the paper, we show that the red line then raises above the blue line. And so model 1 is better than simple means. However, model 2, the green line is better than both. And that's because we are shrinking towards additivity, and additivity is 90% of what's going on. And we can estimate that pretty reliably. And so again, it's saying that model 2 is the best, then model 1 than simple means. Then the last bit of analysis that we do, and then I'll conclude, is we ask, well, okay, George, you show me what happens for the distribution as a whole, but what about what happens for a single specific intersection of interest, maybe intersection 37, okay? So at this point, I should say and acknowledge that as well as obviously the earlier work that Kate was showing in the parallel session with her simulation studies, there are some other simulation studies out there. And this one here in epidemiology in 2022 compared MAIHDA model 2, the accuracy of making predictions for a given intersection with what they call cross-classification, which is just my simple means. And they compared them in terms of something called MSE, mean squared error, which is the measure of accuracy. The lower the mean squared error, the more accurate the method. And you can see here, MAIHDA model 2 does much better than the simple method. But what they don't do is they don't also include MAIHDA model 1. Also, beyond simply just saying, hey, MAIHDA model 2 is better because of shrinkage, that's the only insight that they give. And so what we do is we do this in terms of the analytic expressions. Mean squared error is actually a function of how biased the prediction is and how variable it is across repeated samples. So we separately derive the bias, the variability, and then we reconstruct mean squared error, and we show how things differ from model 1 as well. And we also show how it matters what the actual true value of the intersection mean is and how that deviates from additivity. That's an important part of this. So again, model 2 is the true model, same setup as before. The main difference is that we now additionally focus on a small intersection of size 10, because once again, if the intersection of interest is big, 50 or 100 people, you're going to get the same answers from all three methods. Okay, so let's focus on a small intersection. So here are some expressions for the bias, but let's plot the bias. And so what this is showing is that the simple mean is unbiased. The bias is 0, whatever's going on the x-axis. Now, what the x-axis is plotting how the true mean deviates from the model implied mean. And so this is how it deviates from the German national average. So it doesn't matter whether we're considering an intersection who truly is got low outcome, or truly has got really high outcome, or truly is the same as the national average. If we just do the simple mean approach and just average the 10 reading scores, then we have an unbiased estimator, which means across repeated samples, we will, on average, get the truth. But on any given repeated sample, we'll differ from the truth. Now, model 1 is the red line. And here, if the true mean is below the German national average, we're going to be biased up towards the German average. That's shrinkage. And so that's saying that MAIHDA model 1 actually gives biased predictions. And likewise, if the true mean is above the national average, you get pulled down. So that sounds bad. We don't like bias, but we'll see it's compensated by lower variability shortly. Model 2 is that the true mean is deviating from the model implied mean, is deviating from additivity. Now, those deviations are pretty small, which is why that green line is drawn over a much shorter span. But the reliabilities, the conditional ones, are much lower. And so, so there's those two differences kicking in there. But in general, we'll see less bias from model 2 than model 1, but still more bias than simple means. So actually, simple means or descriptive statistics wins if our only criteria that we care about is bias. But that brings us on to the second criteria, which is to what extent will we get the same answer if another researcher comes along and collects the data in exactly the same way, but gets a different random sample of individuals from each intersection. This is what we get back, which is across repeated samples, that simple mean, it might be unbiased, but it's all over the shop. Sometimes you're way above what you should be, sometimes you're way below. MAIHDA model 1, whilst in general you're going to be biased, actually things aren't going to bounce around so much from repeated sample to repeated sample. So you're getting a little bit more consistency in your answers, and even more consistency, less variability in model 2. So in terms of variability, model 2 is the winner, model 1's in second place, and the simple means are worse. Then mean squared error puts those two things together, because the mean squared error is variance plus bias squared. So that's those expressions. You plot those, and we get smiley faces. So the simple mean is a horizontal line because bias was constant, and so was variance. So you put them together, it's still constant with respect to how the true mean deviates from model implied. But model 1 and model 2, those had biases, linear biases, which are then become quadratic expressions because the bias gets squared into the mean squared error term. And what we see here is, apart from a few cases where the true mean is way different from the model implied mean, okay, you're going to get lower mean squared error and therefore higher accuracy with model 1 versus simple means, and there's even better accuracy for model 2 versus model 1. And so, so this is saying that just like the previous simulation study found, yes, model 2 is better than simple means, but actually what we're showing here is it depends on what the actual true value is and how it deviates from the model implied. Okay, model 1 sits in between those two things, but we've brought clarity in terms of the bias and variance. So just to sum up, with the means of a kind of some kind of target practice or darts board, simple means a bit like shooting at a target board, and on average, those 10 attempts to shoot the target, on average, we've hit the bullseye. Okay, but in reality, we've only got one shot, and that one shot could be anywhere. Okay, and even missing the target entirely. So that's not a great approach. Model 1. Across repeated samples, we're always hitting the target, but we're always a bit off. but there's quite a lot of consistency in where we're at. And so that seems more desirable. If you only have one shot, I'm more confident that it's going to be closer to the bullseye than over here. Model 2, I'm even more confident again because the bias is reduced and the variability is reduced further. So Model 2 is considered the most accurate method to try and hit the target if you've only got one shot. That's effectively what was said in this last part of the talk. So just to conclude, MAIHDA, as you've seen from several talks, is very popular at the moment. It's really an exploratory descriptive approach. It's quite appealing because it has these nice effect size metrics, the VPC and the PCV. It's quite appealing because it gets this league table of intersection means out, which has these desirable statistical properties, which I've been focusing on today. Most applications have been social epidemiology, but I've shown you one in education, which is my own area. And there's no reason why we can't see more applications in social sciences more generally. In terms of my analytic expressions, they show quite conclusively that the Model 2 means are preferred to those in Model 1. And both MAIHDA models are preferred to simple means. But most importantly, this choice of method only matters when intersection sizes are small. And if they are small, they're also a function of VPC. The smaller the VPC, the more choice of method matters. So the smaller the intersectional inequalities are. And they also matter in terms of imbalance and PCV as well. Finally, yeah, tutorial paper, once again, go there if you want to learn more about the MAIHDA method. And on Stock Archive is the full-length treatment. You thought what I just said was long. It's 84 pages, the working paper with appendices. But that's up there for those who are interested. Thank you very much for listening.